Okay, would somebody like to say what they're thinking? What's the idea? Right. I'm trying to show that f is continuous. Right. So, in other words, that we're drawing this like this. That at every point, I'm given any epsilon, you can find a neighborhood around x where all the values of f are within epsilon of f of x. Right? That's what continuity at a point means. You have to show continuity at each point, right? So in other words, for each x given any epsilon, there exists some neighborhood of x in which f of, let's call this point x naught maybe, to make it easier for notation, in which f of x is in the epsilon, is in the epsilon neighborhood of f of x naught. Right? Sam, you had your hand up?
Oh, I was stretching.
Oh, stretching. Yeah, Alex.
Give it a go.
Okay.
I said, suppose f is not continuous.
Okay.
Then there must exist some small epsilon where no f of n could be contained in the neighborhood.
Neighborhood of what?
The epsilon neighborhood of at that point. So say it's not continuous at x naught, then with a small epsilon, f of n cannot exist in that neighborhood.
So you're saying, well, look, we've got
if
this.
f of n is uniformly continuous.
Mm-hmm. So you're saying, well, look, we've got this limiting function f, right? We have this point x naught. Let's suppose we're not continuous there, right? It has some value, f of x naught. And to be discontinuous means that there's some epsilon where you can't find a neighborhood that works, right?
Right.
Right. So there exists some epsilon. Let's call it epsilon. There exists some bad epsilon. Okay. Such that there is no delta neighborhood of x naught in such that f of x lies in the epsilon naught neighborhood of f of x naught for all x in that neighborhood. Right? In other words, in every delta neighborhood, right, to translate a little bit farther, in every delta neighborhood, there's some point, there exists a single point, a point x of delta, say, such that f of x of delta is not in the epsilon naught neighborhood. Right? Right. In every, that's what discontinuity would mean, right? That in every delta neighborhood, there's some point, so that there exists a bad epsilon. Here it is. There exists a bad epsilon, so that in every delta neighborhood, there exists a bad point, which we're going to call it x delta. A bad point meaning a point where we're not in the epsilon world there, right? Where f of x naught is not there. Okay. So where do you go from there?
Yeah, let's see. So then I said, if all f of n are uniformly continuous.
They're not. They converge uniformly. They're not uniformly continuous. They converge uniformly, right? They converge. They're continuous.
Oh, sorry. That's what I meant. Sorry. Since f of n are continuous.
Yes.
For this small epsilon, they couldn't be contained in the neighborhood. I didn't write it very like you would write it.
That's all right. That's
But,
right. Tell me. That's all right. The idea is what counts.
Yeah,
right?
kind of the idea. I feel.
Yeah. So your idea is that, well,
That if the epsilon or if the neighborhoods are super small around, like the tube around F is really small, then if F of n are continuous, it'd have to jump through a point that's outside of the tube.
okay. Okay. So let's think of how to make that precise, right? What you're saying, I think, is that, well, these guys, the f of n converge to f uniformly. So they lie inside of a tube, right? So so they lie inside of an epsilon tube around F.
How do
right?
you express that?
That's just part of this thing here.
Oh, okay.
That's just what uniformly means,
okay.
right? That for all epsilon greater than 0, there exists an n such that n greater than n implies that f n x minus f of x is smaller than epsilon for all x in our domain.
Oh, okay.
Right. Okay. Yeah, I think you can do this, right? Does anyone see how to close it up? How to finish it off? Right. We have this. What we have are, we can take our deltas to be 1 over n, say, right? So for each x plus 1 over n, right, there's a x sub n. We were calling it x sub delta before. Let's just call it x sub n. There's an x sub n where f lies outside of the epsilon tube, right? So in other words, we've got these guys. We've got these guys down here, x, x1, x2, blah, 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 and they're converging to x naught, right? And all of their values lie outside of the epsilon tube, right? Okay, and now we also have uniform convergence, right? Which means that we can make the f sub n as close to this thing, as close to these values as we want, right? Right. Right. So how close do we make it? We'll make it Fernanda?
Third of the epsilon.
A third of epsilon. How about that? Right. Sure. Right. So we take a third of epsilon. We make for epsilon over 3, there exists an epsilon, so that everybody past this point is within epsilon third neighborhoods, right? Okay. And you see that leads to trouble, right? Because that would mean that the function, that all these guys are discontinuous, right? All these guys past this point will be discontinuous, right? Because you see what's happening here. Here's f of x naught, here's the value, right? And here's the epsilon, the bad epsilon. Sorry, it should be epsilon naught. Right? Taking a third of that, right? And so we know that the f sub, right? So for n bigger than our capital N, let's just choose one of them, okay? Choose one of them. Choose some n naught bigger than that n. Choose one of them. We know that the value here lies within, plus or minus epsilon over 3, epsilon naught over 3, right? But we also know that that all of these values at the xn, x1, x2, blah, 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 all the f values lie lie more than epsilon away, right? That means that fn's value right? Fn's values all have to lie smaller than f of x minus 2/3 epsilon, right? Right. So what does that mean? That right, all of fn's values at these points, at the most, are under this. At the most they get close to this line here, right? But fn's value here lies above this line, right? And that means that fn is discontinuous, right? Because we cannot find a neighborhood of x naught in which everybody lies within the epsilon over 3 neighborhood, right? There's all these guys here that right? So you see that fn naught at xi is always smaller than f of x naught minus epsilon 2/3 epsilon naught, right? So you have all these guys that are outside the 2/3 epsilon neighborhood, right? But that means that if we take, so there is no, so taking, there is no neighborhood of x naught in which there is no neighborhood of x naught such that f of x minus fn naught of x minus fn naught of x naught is always smaller than epsilon over 3, right? Because we always have these guys that are more than 2/3 epsilon away. Okay, so it's going to be, so if the limit guy is discontinuous, that forces at least one of the guys, and in fact infinitely many guys, infinitely many of the sequence to be discontinuous also. Okay, so yeah, great. Did anyone do it in a different way? Yeah, Adam.
I did it directly using the triangle inequality.
Yeah, that's another way. You can use the triangle inequality. This is fine. This is fun. This is instructive. Could also use the triangle inequality. Say, well, look. So what did you say, Adam? Tell me the idea.
Basically, I said, okay, we want to show that given some epsilon greater than 0, we want to be able to find some delta greater than 0, such that if x minus y is less than or the distance between x and y is less than delta, then the distance between f of x and f of y is less than epsilon. And then I said, okay, we have so then I basically said, okay, so we have a distance between f of x and f of y, and it's going to be less than the distance between f of x and f of n of x, f sub n of x, plus the difference between f sub n of x and f sub n of y, and the distance between.
Wait. Start over. So say it again. The distance between f of x naught and f of y is smaller than
the f of x naught minus f sub n x naught.
Great. Yeah.
Plus the distance between f sub n of x and f sub n of y, and then lastly f sub n of y and f sub y.
Great. Great. So yeah, and then you did your typical epsilon control. So you said, okay, look, this is the thing that we're trying to make small, right? This is the thing that we're trying to make small. We're trying to find a neighborhood in which this is small, right? Well, we know that the f sub n's converge to the f uniformly, right? So we can find, if we choose a big enough n, then these things can be made smaller than epsilon over 3. Right, so choose n such that the distance, such that fn t minus f of t is smaller than epsilon over 3 for all t in our domain. Right, that'll make this and the first and last term smaller than epsilon over 3. Right? You've chosen the tube to be epsilon over 3, and then you know that there's got to be somebody in the tube. Right? Eventually, everybody's in the tube. Just choose one of those guys. Okay. Further, you know that this guy is continuous, right? Since Fn is continuous, you know that continuous at every point, in particular x naught. You know that there's a neighborhood where you can make if y is in that neighborhood, then this thing is smaller than epsilon over 3. Right? There exists a neighborhood of x naught in which all f of y's, all f and y lie in the epsilon over 3 neighborhood of f and x naught. Okay, so that's the neighborhood you want, right? You see that in that neighborhood, the distance of x naught, f of x naught from f of y is smaller than epsilon over 3 plus epsilon over 3 plus epsilon over 3. So that's it. That'll do. Okay. Everyone all right? Anyone have questions? Okay, let's go on. So this is one of the properties of uniform convergence that we desire, right? That it preserves continuity, right? And that it also preserves a bunch of other qualities. So yeah. Okay. So that was the following, which in the book is listed as a corollary. Right, if you have a sequence of functions, and the Fn are continuous, and the Fn converge to F uniformly, then F must be continuous also. And that's given as a corollary to the following theorem, which goes like this. So you have a sequence of functions, and x a limit point of the domain. If Fn converges to F uniformly on E, then the limit of f of t as t approaches x equals the limit, is the same thing as if you took the limit of each of the functions as t approached x, and then took the limit of that as n went to infinity. Okay, so you see that if everybody is continuous, what does this say? This says that the limit of this function, if each of these guys is continuous, then this thing is going to be fn of x, right? This thing is going to be fn of x, and what this would say is that the limit as n goes to infinity of fn x equals the limit of f of t as t goes to x. But the limit of the fn x is f of x, right? Which is, so this is by definition f of x, right? So that would say exactly that the limit function is continuous, right? The limit of f of t as t approaches x is the value of f at that point. So if fn are all continuous, then this would say what this would give us the corollary. Okay. Mia. Yes? You're looking like you're thinking about something.
The joys of mathematics.
The joys of mathematics.
Yeah.
Wonderful. Okay, so the proof of this is almost along the same lines as what Adam was suggesting. So let me just go through it quickly. I don't even know if we need to do it. Let me just do it. Okay. So first thing we're going to do is consider. So let a sub n denote the limit of the s of n as t goes to x. Okay. This is what would be fn x if it were continuous, right? This would be fn x if these functions were continuous, but but our x isn't even in the domain, so it's just the limit of that function, the limit of those functions. Okay. And the first thing we're going to notice is that this converges. The claim that the an converge, this sequence converges. Okay. And the proof of this is simple. You want to show that the sequence is Cauchy. Want to show that the an sequence is Cauchy. But you know that these guys converge uniformly, right? So you say, well, so given epsilon bigger than 0, since we have uniform convergence, we know by the Cauchy criterion that there exists some n such that for all n and m bigger than n, we have that fmt minus fmt is smaller than epsilon over 2 for all t. And that will give us that the a sub n are Cauchy, right? Because this is true for all t. So let t go to x. Take the limit, then take the limit as t goes to x, and we get that an minus am is smaller than or equal to epsilon over 2, which is smaller than epsilon. I use the epsilon over 2 because when you take the limit, you might get equality. I want less than. Doesn't matter. It's not that important. Okay, so this is just to substitute for the fact, if we had continuity, then we would just say, well, we've got we have that the uniform convergence, and so we have convergence of the values. But since we don't have continuity, since we don't have continuity of those functions, we need to make sure that the sequence converges. So that's all that's for. And then the rest of it is basically identical. So you say, okay, the distance takes epsilon greater than 0. The distance between this and A, so so the AN is Cauchy and converges to some A. And our goal is to see that the f of t approaches A. Right? In other words, to find a neighborhood around f of x, a neighborhood around x in which where f of t is within epsilon of A. It's just like we were doing before. Right. We want to find some neighborhood of x in which f of t lies in the epsilon neighborhood of A. Okay. Is everyone following? Anybody lost? Anybody lost? Okay, so you do basically the same sort of thing. You say, okay, well, this is controlled by the distance between f of t and fn of t plus fn of t and a sub n, right, which is its limit as t goes to x, right, plus the distance between a sub n and a. Right, this in what we did previously, we had an fnx here, right? It's basically the same thing, just the limit of fnt as t goes to x. Okay. And you just do the same thing, right? You say, okay, well, look, we know that since the f sub n converge uniformly to f, and since the a sub n converges, this is a sequence converging to this value, right? There exists an n such that, there exists a capital N such that n bigger than n implies that this thing is smaller than epsilon over 3 for all t, right? And this thing, and this thing is smaller than epsilon over 3. Right? And then, just like we did before, continuity allows us to say, no, not continuity. Since the limit of this is a sub n, right? Further, since the limit, so fix and bigger than n, choose one guy. Since the limit of f sub n is a sub n as t goes to x, we know there's a neighborhood in which this thing is small. So make it smaller than epsilon over 3, and then that's the end. There exists a neighborhood of x in which the distance of fnt from a sub n is smaller than epsilon over 3. And then, so in that neighborhood, we see that the distance of f of t from A is smaller than epsilon.
Just like a notational question.
Yeah.
Could you say that instead of epsilon over 3 for all of them, you just said epsilon and then at the end say less than 3 epsilon?
you could say less than 3 epsilon, and then say since epsilon was arbitrary,
Yeah.
you know, it doesn't matter.
Yeah.
Yeah, yeah. That's all been done. But yeah, it's just to, you know, make it in perfect accordance with the phrasing of the definition. But it doesn't make any difference at all. Yeah. Yeah. Yeah, certainly if you can bound it by some multiple of epsilon, then that's enough. Okay, is everyone okay? Are you all right? You don't look well. Why don't you look well? I don't know. You should be at least a little bit cheerful.
Why?
Because we're alive.
Oh.
Because the world is amazing. I love that. Okay. Okay. So next result. So to motivate this, let's think back to recall that if we looked at this set of functions where f of n was x to the n, then these guys are all continuous, right? These guys are all continuous, and okay, let me say it this way. They're all continuous, and they converge pointwise. And they converge pointwise on a compact set, right? It's not just any set. They converge pointwise on a compact set. However, they don't converge uniformly. They don't converge uniformly, right? The thing, you know, that was the moral from last time. So converging pointwise on a compact set, you know, this is the main thing. Converging pointwise on a compact set doesn't guarantee uniform convergence. So converging pointwise on a compact set does not imply uniform convergence. Right? And I said that a lot of what we're going to be doing in the next couple of weeks is you know, when can we get uniform convergence? Suppose you start off with a pointwise convergence set, pointwise convergence sequence. When can you get a uniformly convergent subsequence? We'll start off with a kind of cute result in that direction. Okay, so here it is. Suppose you have Fn that converge to F pointwise on some set K. Okay. And suppose you know that f of n and f are all continuous functions. And you know that they are decreasing. At every point, you've got decreasing values. Okay. And you know that that K is compact. Then, in fact, uniform Fn converge to F uniformly. Okay. So says that we were really close with this example, right? Continuous functions converge pointwise. These guys are decreasing, right? At each point, the values are decreasing as we increase the numbers, right? And it's a compact set. The only thing that messed up is, the only thing that we don't have is that the limit is discontinuous here. Okay, and that you know. So you see that this really does need to be continuous. And if this is not continuous, then we can have examples where the convergence is not uniform. Okay, and you'll see why. You'll see why that's crucial in a second, as we run through the proof. Okay, so we want to show that it converges uniformly. In other words, we want to show that given any epsilon exists in n, such that n bigger than or equal to n implies that fnx minus fx is smaller than epsilon for all x in k. Notice that, so observe that it suffices to show that there exists a single n such that fnx minus f of x is smaller than epsilon for all x in k. Because these guys are decreasing down to f, right? So the distance between them is the distance between them is not only positive, so we can get rid of the absolute values, but it's also decreasing, right? They're going downwards to f, so the distance is shrinking. So if at some point it gets smaller than epsilon, then after that point, it's all going to be smaller than epsilon. Okay. Everyone all right? Okay. So, so we do something pretty cool, which is the following. Let k sub n be the set of points in K where f sub n minus f of x is bigger than or equal to epsilon. So for each function f sub n, we look at the we look at the points where the difference is bigger than or equal to epsilon. Okay. And our goal is to show that there's got to be one of these guys where this is empty, right? If we show that there's a place, you know, there's one function, there's one of these guys where there's no point where this happens, then it must be that all points the difference is less than epsilon, right? If there's no points where the difference is greater than or equal to epsilon, it means that at all points the difference is less than epsilon. Okay, so that's our goal. We want to show that Kn is empty for some n. Okay. Okay. So notice that the Kn are nested. Right? Because if the distance between fn plus 1 is, the difference between fn plus 1 and x is smaller than the distance between fn and x, right? So if this is bigger than, if the distance between fn plus 1 is bigger than epsilon, then certainly the distance between fn is going to be bigger than epsilon, right? So it's nested. Okay. 2, if we take the intersection of all Kn, we see that that's empty, right? Why? if you look at a single point, eventually this thing is going to have to be smaller than epsilon, right? Because we have the Fn converge to F. Right? The Fn converge to F, so you can't be, your distance from F can't be greater than epsilon forever. Right? It's got to become smaller than epsilon eventually. So there's no point that lies in every case of N. Okay. Okay. What's the last thing I'm going to say?
Can you explain that one more time?
Sure. Right. The case of N are the points where the distance between f sub n and f is big. Okay? But at every point, fnx turns into, converges to f of x. Right? So at some point it has to get smaller than this epsilon. Epsilon is some fixed number. Right? It's got to be smaller than epsilon for that to be true.
Yeah.
Right? We assume that we have convergence to f. Okay. So what's the last thing I'm going to say here? What? Triangle inequality? It's one word. You can't mix that. You can't stick that word together.
So that's what you doesn't. One of the KNs have to be empty because we had some theorem that said that the intersection of a bunch of
What kind of sets?
compact
sets. Right.
Okay.
So Kn are compact. That's the word. The Kn are compact. Why? The K is compact.
Closed subset of.
It's a closed subset. Why is it a closed subset?
Because they're nested?
Because they're less than or equal to epsilon. This difference function, the Fn is continuous. F is continuous. The difference function is also continuous. Right? The difference function is also continuous. You're taking the inverse image of epsilon infinity. Epsilon infinity, which is a closed set. Right? Epsilon infinity closed. Taking the inverse image of epsilon infinity, which is a closed set. So you get a closed subset of a compact set. Okay.
How is that closed?
How is this closed?
Well, it's just because you said it's
Sorry.
greater than or equal to epsilon.
Yeah, because it's greater than or equal to. Yeah. Or think, what's its complement? This, which is clearly open. Me.
Is it just a convention? Wait, are you treating like the positive infinity part as closed, but the negative infinity? Okay. And then you think it's
Remember what open means, right?
Yes.
Open means that every point is interior. Every point is interior.
Yes.
Okay. So the complement of this, clearly an open set.
Okay.
So this guy is closed. Okay. So what do you see here? If these guys satisfy, if the Kn satisfy the finite intersection property, then we know that the intersection of the Kn would be non-empty. Right? That means that they cannot satisfy the finite intersection property. That means that some finite intersection of these guys is empty. Since they're nested, that means that one of them must be empty. If they satisfy the finite intersection property, the intersection would be non-empty. But it is empty. So they must not satisfy the finite intersection property. that means that some finite intersection of them must be empty, right? And since they're nested, that must mean that the smallest guy of that set is empty. Okay. So it's cute, right? I feel like this one is cute proof.
And so we're showing that it's
So-
empty.
Right, so showing that it's empty means that at some point, the distance between Fn, for some n, the distance between Fn and F must be smaller than epsilon.
Mm.
And since that distance is decreasing, we know that past that point, the distance is also smaller than epsilon. In other words, we found the time past which everybody lies in the epsilon tube around F. Okay, so given an epsilon, we found a time past which, or at least we showed there exists a time past which all of the f sub n lie in the epsilon tube. In other words, uniform continuity, uniform convergence. Okay. Any questions about that? Any other questions about that? Okay. So okay. So now we're going to do something that's pretty simple, but sort of like a different point of view about uniform continuity. So sort of a different point of view. It's not all that different, but it's just one way of thinking about this. Okay, so let's start off with let X be a metric space, and let C of X be defined as the function's complex valued function on X such that F is continuous and bounded. So continuous bounded functions. Okay. Second thing we do is for every function in that set of bounded continuous functions, let the norm of f be defined as the supremum of the absolute value of f of x over all values. Okay. And this thing is called the supremum norm. Then, for pairs of functions f and g in C of x, let the distance in that space between f and g be defined as the sup norm of the difference between f and g. I leave it as an exercise to see that this is a metric. So C of x with this metric becomes a metric space. Okay, so we define this, the supremum norm on the space, right? Just the supremum of the absolute values of all values, right? And we define a distance, induced by that norm. Question: what does Fn converging to F in this metric mean? So we have a metric space. We have points in our metric space, functions, continuous bounded functions, right? So we can talk about, these guys converging if within the metric space. What does it mean? Sam?
The supremum norm between Fn and F is going to be less than epsilon.
That's right, we can make that as small as possible, right? In other words, right, given any epsilon, there exists an n such that if n is bigger than n, then the supremum of f of fnx minus f of x is smaller than epsilon. Right? But what is that? That's exactly what we've been calling uniform convergence. Right. So it's just a different point of view, right? Convergence, you have this metric space, you have a metric, you have this set of functions, you create this norm on the set of functions, right? Converging in the metric space sense is the same thing as converging uniformly in the sense that we've been talking about. Converging in this metric means that this distance can be made as small as we desire, right? Well, that's just, what does that mean? That means that the supremum between these two of the difference is smaller than epsilon, right? That means that at every point, right, the distance between these the distance between these functions is smaller than epsilon.
So I had this question, is the supremum norm kind of like the bound on the function?
Yeah. It's just that you may not attain that bound, right? If this, it's, you might not actually attain that value. For example, if you're looking at 0, 1, and you look at the function f of x equals x, well, the supremum, right? The supremum norm of this guy would be 1, even though the function never attains the value 1. Right?
Right. Oh, yeah.
Okay.
Doesn't know what a bound is? Isn't that what a bound is?
Yeah. I'm sorry, I thought you meant a max. Sorry. Yeah.
Oh, yeah, okay. So it's just the, interesting, okay.
It is the least upper bound of all values, all
Right, okay.
absolute
That makes
values
sense.
of values. Okay. Yeah. So, this is just another way of looking at it. Seeing this as a metric space statement rather than as, something that we needed to define independently. Right. We've been talking about uniform convergence, but what we could have done is just said, let's introduce this norm on this space and talk about convergence in the old metric space sense, and we would have secretly been talking about uniform convergence. Okay. Okay. And so that leads us to the following theorem, that the space is in fact a complete metric space. So think about that for a minute and tell me why that's true. I think I have in my notes right here it says make them do it. So.
All quotient functions converge. So
So the limit of f can't be undefined or can't be a function that's not in the measure space.
Okay, talk to somebody nearby if you haven't started talking already. What are you thinking?
Oh, I was just saying it's probably related to the information we were given. But I don't see why.
Yeah. Hold on a minute. Okay. So we want to show, right? Want to show if Fn is Cauchy, then if then it converges, right, to some function in the space. Right. Right. So what does Cauchy mean? Cauchy means that, right, given any epsilon, there exists an n such that n and m bigger than n implies that the distance between Fn and Fm is smaller than epsilon. Right? Okay. Right, so right, the supremum of Fnx minus Fmx is smaller than epsilon. Okay, so what, right? So at least can we say that is it clear that we have convergence at each point? Do we have pointwise convergence? I mean, right? So right, at each point in the space, you see that this sequence, right? So for each x in x, Fnx is a Cauchy sequence. Right. And so it converges to some value. Let's call that value f of x. Right? And right, what we have, this thing here is the Cauchy criterion for uniform convergence, right? So these guys, maybe I don't even need to say this part. The f sub n converge uniformly. right? Because this thing is the Cauchy criterion for uniform convergence. So this is the Cauchy criterion for uniform convergence. So, you know, these guys converge uniformly, right? And what do they converge to? You know, they converge to something that's continuous because of our previous theorem, right? These guys were all continuous functions. They converge uniformly. So by a previous theorem, they converge uniformly to some function f. And by a previous theorem, that f is continuous. I guess there's one more thing we need to say, which is that that function is going to be bounded. But why is that function bounded? Can anyone sort of tell me why that function has to be bounded? Yeah, Reed.
All of the individual functions are bounded? All the f's are?
Yeah, exactly. Right. All the f sub n are bounded, and they converge uniformly to this guy, right? So then, for them to lie in an epsilon tube, for them to lie in an epsilon tube around f, means that this f has to lie in an epsilon tube around one of them, right? And so it'll also be bounded. So
C is defined as all functions that are continuous and bounded.
mhm. Yeah. So yeah, we continuous in that way. Okay. Okay. So what you see is that the space is actually a complete metric space. Okay. So next time we'll talk about uniform convergence and its interaction with integration and differentiation. I haven't taught you about integration, so I'll have to tell you what it means to be integrable. You've probably seen something like it when you were, you know, a child or at least younger. Yeah, we'll just. Okay, that's it for today.